California has always braced for the big one, but scientists now warn the true disaster may not be what we expected. New evidence confirms the next major quake could explode past the seismic speed limit, a supershear event, unleashing a shockwave that doubles the devastation and moves faster than sound. If this warning is right, are our cities prepared for a kind of earthquake we've never truly faced? The answer begins with the science. Imagine a rupture tearing through the earth faster than the very waves it creates. In most earthquakes, the break along a fault, what scientists call the rupture front, moves at a steady pace, always trailing behind the seismic shear waves that ripple outward. These S-waves, traveling at about 3 kilometers per second in California's crust, usually outrun the rupture, spreading energy in all directions and giving cities a few precious seconds as the ground starts to shake. But sometimes, the rupture itself accelerates. When the fault is long, straight, and under enormous stress, the rupture can break the seismic speed limit, racing ahead of the S-waves. This is the supershear threshold, the moment the fault's movement overtakes its own shock waves. Physicists compare this to a jet breaking the sound barrier. When a plane hits supersonic speed, it outruns its own pressure waves, forcing them to pile up into a single explosive cone of energy, the sonic boom. In a supershear earthquake, the Earth does the same thing. The rupture front compresses seismic energy into a narrow high-velocity pulse, a Mach cone, focused directly ahead of the break. This concentrated front is not just a technical curiosity. The shockwave slams into the ground with a force that can double the intensity of shaking, especially along the direction the rupture travels. Instead of the energy spreading out, it is funneled into a single devastating jolt. Scientists call this a ground motion pulse, and it can arrive with almost no warning. The speed is staggering. When rupture velocity passes 3 kilometers per second, the shock front can reach distant neighborhoods before emergency alerts finish sounding. The implications are profound. In a supershear event, the most violent shaking is not always at the epicenter. It can leap ahead, striking cities or infrastructure miles down the fault line with little time to react. This is not a slow build of tremors, but a sudden, focused burst, an earthquake's version of a sonic boom, delivered by rock and fault instead of jet and sky. Understanding this threshold is the key to grasping why a supershear quake can be so much more destructive than anything in the standard playbook. The science of the shock front explains why the next big one could be unlike any earthquake California has ever prepared for. In August 1999, the city of Izmit, Turkey, was jolted awake by a magnitude 7.6 earthquake. The rupture raced along the North Anatolian Fault, but what stunned scientists was the speed it achieved. Instruments recorded the rupture front breaking past the S-wave barrier, accelerating to over 4 kilometers per second. This was one of the first times a supershear event was caught in real time. The destruction was staggering. Concrete buildings pancaked, highways split, and entire neighborhoods collapsed. The most severe damage did not always follow the usual pattern. Instead, it lined up with the path of the rupture's shock front, where the seismic energy had concentrated into a focused ground-level blast. Seismograms from the event revealed a sharp pulse-like jolt followed by chaotic shaking, a signature now recognized as the double strike of a supershear earthquake. Just 2 years later, in November 2001, the Kunlun Fault in Tibet ruptured in a magnitude 8.1 earthquake. The rupture front sustained supershear speeds for nearly 400 kilometers, the longest ever documented. Satellite radar and field surveys traced a scar across the plateau, showing where the Earth had split at supersonic speeds. Villages hundreds of kilometers from the epicenter reported violent, sudden jolts, and researchers pieced together the evidence. This was not just a big earthquake, but a supershear event on a scale never seen before. The shockwave's reach was immense, with the strongest shaking mapped far down the fault's path, not just at the break's starting point. Then, in March 2025, the world's attention turned to Myanmar. A magnitude 7.7 earthquake struck along the Sagang Fault. Seismic networks across Asia and satellite imagery from teams at UCLA and USC revealed something chilling. The rupture had accelerated to nearly 5 kilometers per second, matching the classic supershear profile. The geometry of the fault, long, straight, and under intense strain, mirrored the southern San Andreas in California. Damage reports from Myanmar told the same story as Izmit and Kunlun, entire towns battered by a sudden, overwhelming jolt, then rocked by lingering waves. The data left little doubt. This was another supershear event, and its mechanics were a near-perfect match for California's most dangerous fault. For the scientists watching in Los Angeles, the Myanmar quake was not just a distant tragedy, it was a glimpse into California's possible future, unfolding in real time. Each of these earthquakes, separated by continents and decades, delivered the same warning. When a rupture finds the right conditions, it can break the seismic speed limit, and the results are far more devastating than magnitude alone can predict. Stretching from the Salton Sea to the edge of the Mojave, the southern San Andreas Fault runs in a nearly unbroken line for more than 300 kilometers. This is no ordinary fracture. In seismic terms, it is a perfect runway, straight, smooth, and primed for speed. Dynamic rupture simulations by teams at the statewide California Earthquake Center and the University of Southern California show that when stress finally gives way, there is nothing to slow a rupture down. Unlike faults with bends or kinks, which act like speed bumps, this corridor lets the brake accelerate unchecked. The Mojave segment in particular stands out in every model. Here, the fault is so linear that a rupture can reach supershear speeds within seconds, sustaining that velocity for the length of the segment. Computer models run scenario after scenario. The most likely nucleation point lies near the Salton Sea, where decades of strain have built up. Once triggered, the rupture can shoot northwest, racing at over 3 kilometers per second, sometimes even faster. The odds are not remote. Recent analyses estimate that 1 in 3 major strike-slip earthquakes worldwide go supershear. In California, the geometry of the southern San Andreas makes that probability far more than a theoretical risk. Every kilometer of straight fault is a potential launchpad for an earthquake that could outrun our warnings and overwhelm our preparations. When a supershear rupture ignites near the Salton Sea, the shock front does not just radiate outward, it targets. The fault geometry funnels seismic energy, forming a cone of destruction that aims straight at the Los Angeles basin. This is not a diffuse wave. It is a focused pulse, like a battering ram slamming into the earth. Dynamic rupture simulations from SCEC and USC reveal that as the rupture races northwest, the most violent shaking follows the fault's path, not its edges. The ground in the direct line of fire, cities, suburbs, and infrastructure, will feel the first jolt as a sudden, almost explosive impact. Then, as the energy enters the deep sediment of the basin, the shaking does not just stop. Instead, the soft layers trap and amplify the waves, prolonging the motion and multiplying its strength. In these scenarios, peak ground velocities in downtown Los Angeles can double or even triple compared to areas outside the energy beam. The city's dense core, built atop ancient riverbeds and filled with millions of people, sits in the crosshairs of the supershear funnel. The lived experience will not be a slow rumble, but a split-second shock, immediately followed by rolling chaos that lasts far longer than the initial blast. This is the geometry of disaster, delivered by rock, fault, and the physics of speed. California's seismic safety codes were written for a different kind of earthquake. Decades of engineering assumed the harshest shaking would come sideways, perpendicular to the fault. But supershear quakes hit differently. Their most violent force travels forward, parallel to the fault's path, hammering buildings, bridges, and pipelines in ways they were never designed to withstand. The gap is not theoretical. Across the southern San Andreas, dozens of lifeline crossings, highways, aqueducts, transmission towers remain unretrofitted for this forward-directed shock. State engineers have warned that even the Colorado River Aqueduct, which supplies water to millions, could be severed by a rupture near the Salton Sea. Early warning systems such as Shake Alert, tuned for slower ruptures, may not deliver alerts before the shock front arrives. In October 2025, the statewide California Earthquake Center issued a blunt directive: update hazard maps, re-examine every critical crossing, and rewrite building codes to account for Supershear's double strike. Dr. Yehuda Ben Zion put it plainly: "We cannot say exactly when and where the next earthquake will be, and we cannot say which one will be Supershear. But we can say with certainty that over the next few decades, we will have multiple magnitude 7 earthquakes in California. They are coming, whether we are prepared or not." 1/3 of major strike-slip earthquakes worldwide has now been confirmed as Supershear events, and the southern San Andreas Fault matches every condition seen in past disasters. Records from Izmit in 1999, Kunlun in 2001, and Myanmar in 2025 provide undeniable evidence. When the rupture exceeds the seismic speed limit, the damage is far beyond standard expectations. Yet, despite these warnings and the 2025 statewide California Earthquake Center directive, California's building codes and critical lifelines remain unprepared for the forward-directed shock front of a Supershear quake. Scientists have mapped the Strait Mojave corridor and demonstrated through high-resolution models how energy would funnel directly into Los Angeles. However, exactly when and where the next rupture will occur remains unknown. The documentation is clear: the risk is not hypothetical, and the window for preparation is closing. As the statewide California Earthquake Center states, multiple magnitude 7 events are certain in the coming decades. The evidence leaves no room for delay, only for action.